Hi, I'm Tong Li from Huawei. Today I'm going to introduce TACK, Improving Wireless Transport Performance by Taming Acknowledgments. High throughput transport over WLAN becomes a demanding requirement with the emergence of applications such as UHD wireless projection, VRR-based interactive gaming, and so on. However, the current WLAN connection speed is still far from satisfactory for UHD video-based applications. Most modern WLANs are based on the IEEE 802.11 standards. It is well studied that medium access overhead in WLAN can significantly reduce TCP throughput. This is because TCP ACKs cause internal interference on the same connection. It is also well studied that the overhead for sending each packet is independent with packet size. ACKs cause almost a similar medium access overhead despite the much smaller size. As a result, the internal interference between data packets and ACKs is non-negligible. To explain the internal interference more clearly, we conduct emulations over wireless links. Basically, TCP sends an ACK for every 1 or 2 packets, which is frequent. As shown in the left figure, the throughput on the ACK path is relatively low. However, as shown in the right figure, the throughput on the data path decreases significantly with the increase of ACK frequency. In wireless scenarios, reducing ACK frequency has a positive effect on the transport performance due to the reduced contentions. Unfortunately, simply reducing ACK frequency hurts TCP performance, which is called negative effect. This negative effect is because that TCP's transport control depends on frequent ACKs, and the packet clocking algorithms are impacted when the ACK frequency is excessively reduced. In this case, acknowledgments should be tamed. This paper aims to seek the optimal ACK frequency with corresponding improvements in the transport mechanism to avoid the negative effect. And here are the takeaways. First, legacy TCP's delayed ACK cannot ensure minimal ACK frequency. It is far from being optimal. Second, our way of avoiding negative effect is not only TACK, but also a TACK-based acknowledgement mechanism. Third, a transport protocol applying an approximately minimized ACK frequency works better than expected. Let's start from the first one. Legacy TCP alternatively adopts delayed ACK, in which a data receiver may delay sending an ACK for every L4-sized incoming packets, or by a given time interval. When data throughput is high, the ACK frequency still might be large. On the other hand, when data throughput is low, the ACK frequency is always as high as that in the case of a high throughput, which wastes resources. This reveals that the frequency of TCP's delayed ACK is not bounded or not minimized under bandwidth change. In other words, TCP's delayed ACK is far from being optimal. We propose TACK, a new acknowledgement whose frequency is decided by BDP, the bandwidth, and the delay product. The frequency of TACK is the minimal value between byte counting ACK and the periodic ACK. Specifically, TACK applies periodic ACK when BDP is large, and falls back to byte counting ACK when BDP is small. In this case, when data throughput is high, the ACK frequency is bounded. On the other hand, when data throughput is low, the ACK frequency is reduced proportionally. To conclude, our first takeaway is that TCP's delayed ACK is far from being optimal. This is because TCP adopts a max function other than a min function. However, our work in this paper has demonstrated that a min function is also able to achieve good transport performance. The key is to avoid TACK's negative effect. Then we give the second takeaway. Instead of simply applying TACK, a carefully designed TACK-based acknowledgement mechanism is the way to avoid TACK's negative effect. Here we list several major issues to handle in terms of loss recovery, round-trip timing, and send rate control, including congestion control and flow control. For detailed case studies of these issues, please refer to the paper. To solve these issues, we propose a full TACK-based acknowledgement mechanism. There are some notable features of this mechanism which are important for reasoning about the differences from legacy TCP. First, apart from the ACK type of TACK, we also introduced the ACK type of IACK to assure timely feedback upon instant events. IACK and TACK are complementary. IACK assures timely signaling, while TACK acts as the last resort mechanism in the case of ACK loss. Second, when the loss rate on the ACK path has reached a critical level, TACK should carry more information, such as continuous range of lost packets or received packets. With more types of ACKs and more necessary information carried in ACKs, the TACK-based acknowledgement mechanism, therefore, is able to send less number of ACKs, but are exactly what are required by transport. We further give the protocol design of the TACK-based acknowledgement mechanism, in which the advancements in loss recovery, round-trip timing, and send rate control are the most key reasons that TCP's dependence on frequent ACKs has decreased. For more technical details, please refer to the paper. To summarize, applying TACK significantly reduces ACK frequency and improves performance ideally. However, simply applying TACK probably falls short. What we really want for WLAN is a full TACK-based acknowledgement mechanism that overcomes the hurdles for applying TACK, using an approximately minimized ACK frequency to support efficient transport. We have conducted experiments on both wired and wireless links. The results show our third takeaway. A transport protocol applying an approximately minimized ACK frequency works better than expected. We implement TCP TACK, a TCP implementation that applies TACK and deploys the advancements as specified above. We co-designed the receiver-based BBR as a TACK-based congestion controller. Here is the result. TCP TACK achieves significant advantages over legacy TCP in WLAN scenarios due to less contention between data packets and ACKs. Specifically, TCP TACK reduces over 90% of ACKs and also obtains an improvement of 28% on good put. We further find TCP TACK performs equally well as high-speed TCP variants in wide area network scenarios. This is attributed to the advancements of the TACK-based protocol design in loss recovery, round-trip timing, and send rate control. This reveals that an approximately minimized ACK frequency works better than expected. I would like to conclude today's talk by summarizing the takeaways. First, TCP's delayed ACK is far from being optimal. Instead, TACK adopts a mean fraction to assure the minimized ACK frequency in the context of network dynamics. Second, our way of avoiding TACK's negative effect is a TACK-based acknowledgement mechanism in which we define more types of ACKs and carry more necessary information in ACKs, and then we are able to send less number of ACKs. Third, an approximately minimized ACK frequency works better than expected. TACK-based protocol provides a good replacement of legacy TCP in WLAN and also works well in WAN scenarios. Moreover, TACK and its corresponding improvements in transport mechanism can be also adopted into other stacks, such as QUIC, to compensate for scenarios where the acknowledgement overhead is non-negligible. This work is also being discussed in the IETF working groups. Please get in touch and we will be happy to discuss with you. Thank you for your watching.
Excellent. So we have two questions in the chat, which are interestingly enough, kind of the same question, which should be great for having a little discussion here. And those questions are basically, in Wi-Fi 6 and in cellular networks, we get the ability, I'm summing up what Yunfei and Kastuba Jane said, Yunfei Ma. What we're looking at is a future where scheduling is starting to enter Wi-Fi, where it's not necessarily going to be the case where we are going to have contention with acknowledgements anymore. They might be slightly more scheduled. And I'm curious, in terms of cellular and Wi-Fi, the future of them, do we see that TACK is going to be needed? How will it work in the future of cellular and Wi-Fi?
Yeah, this is actually, it's a very good question. And actually, TACK is designed especially for the WLAN, but actually it's TACK and its corresponding advancements can also be adopted in scenarios where the acknowledgement overhead is not negligible. So actually for cellular network and or other networks, also Wi-Fi 6, for cellular network, actually the contention between data packets and ACKs is less. The contention is less than the WLAN scenarios. But actually we can see for cellular network, the uplink is usually, the bandwidth is usually limited. So for asymmetric bandwidth scenarios in the cellular networks, maybe reducing the ACK frequency also can solve some problems when the ACK path is congested. So for Wi-Fi, another scenario, another question is for Wi-Fi 6. Actually, I know Wi-Fi 6 is using the OF DMA, this kind of new technologies in the LTE. So actually, I agree with that. Maybe the problem is not so serious in the Wi-Fi 6, but actually we can only say the contention is less, but the contention always exists. So we also have a conclusion that when the physical rate increase, then the advantage of the TACK by reducing the ACK frequency it will increase. So actually in Wi-Fi 6, because of the bandwidth is enlarged, so our benefit from reducing the ACK frequency will also be enlarged.
Excellent. Just to save time, jump to the next question. So this is from Carrie Williamson, and basically said, so for multi-hop wireless networks, actually this contention between acknowledgements seems like it would be even bigger and even worse problem. And
yes.
Do you have any sense of how well TACK works in that scenario? Have you guys tried it at Huawei? That kind of thing.
Actually for ad hoc networks, I didn't have the test data, but in theory, the benefits of the TACK will also increase because the interference is more serious. I think in the future we might give this kind of test data. I think this is a very interesting topic to investigate.
Okay, and I see Aruna is typing a question, I think, and we have a minute remaining, so we'll wait to see if Aruna says the question. Let me just look really quick. That was my kids blowing up something in my house. I can also ask something super quick while we're waiting, which is basically on wide area network links, was TACK much more difficult to debug than other protocols? Like, because with TCP, you have a pretty simple, it's going to acknowledge after 1, 2, or 3 packets, and TACK, it's a little more complex. So was it hard to figure out where performance issues were happening in wide area networks?
Maybe, yeah. Actually, because we reduced a lot of, maybe over 90% of the number of ACKs. So if you want to just, according to the connection, connection state, it is true that it will be more difficult, but actually because TACK carries more necessary information in the ACKs, so the size of the ACKs is larger than the traditional one actually. So it is more informative. So with the necessary information in the TACK, the endpoints can also get the most of the information needed for the connection.
Okay, great, Tony. Basically, it's a very clever idea, and but I'm thinking, is there any way you basically apply that to the window-based protocols? But how do you think about there's still quite a lot of protocol based on the rate. For example, in a local area, maybe we have this ROCKY that's based on the rate-based congestion control. So is there any way to apply, say, giving the better and just enough feedback from the network or the receiver? Yeah. Any thought on this?
Yeah, actually this is a very good question, and actually because we in TACK we send less number of ACKs, so in this case, the sender will have less information to do congestion control. So also it will result in some burst for the window-based congestion controllers. So actually, TACK is more suitable for the rate-based congestion controllers, such as, for example, we are using the BBR as our first implementation for TCP TACK, because BBR, they have the pacing as a basic mechanism for the sender. So the pacing can avoid the large burst for sending less number of ACKs.
Right. Yeah. That's correct. Yes, and I think it's you have pacing is better than this burst. Okay.